Hi, I'm Anay Mehrotra. I will be talking about our paper titled Fairness for AUC via Feature Augmentation. This is joint work with Hortense, Fong, Vineet, Kumar, and Nisheeth Vishnoi at Yale University. Recent work has shown that traditional classification methods can have disparate performance across protected groups such as people of a specific race or gender. This has led to rich research in developing solutions for fair classification. However, a major challenge in their real-world deployment is that they assume the training data is sufficiently predictive for all protected groups. This may not be true if data is collected to optimize productivity for the majority group. And a recent survey of practitioners found that most of the errant reviewees seek guidance at the data collection phase rather than at the model development or training phases. The question is that which data should you collect or acquire in order to ensure that the classifiers trained on these data are fair? Before considering potential approaches, let's look at a model of data. There are n acquired training samples where each training sample contains a class label y to be predicted, a predicted attribute a, and a feature vector x with b features. All of this data has already been bought or collected by the manager. In addition, there are m minus d unacquired auxiliary features that the data manager can buy. We'll focus on classifiers formed by thresholding generalized linear models, or GLMs, and later consider extensions to other classifiers. For a classifier f, we measure its predictive performance using AUC, that is the area under the receiver operator curve of f, and measure its bias using a metric based on AUC. The bias metric measures 1 minus the ratio of the minimum AUC of f across groups and the maximum AUC of f across groups. Intuitively, this value is close to 0 if f has a similar AUC on each group, and close to 1 if the AUCs of f vary significantly across protected groups. The challenge in deciding which features to acquire is that before purchasing the feature, the data manager only has access to the first few movements of the data from the data brokers. We study this problem under a binormal framework of data, where conditioned on the class label and protected attributes, all features are drawn from a multivariate normal distribution. Under the binormal framework, the AUC of the best generalized linear model has a closed form expression in terms of the first and second moment of the features. This expression has been observed to be robust to deviations from the binormal framework. The benefit of having this expression is that the data manager can use it to estimate the resulting AUC before acquiring the features. Still, there are many approaches between which can be used to acquire the data. For instance, a natural approach is to acquire features that minimize bias according to the expression according to this expression of the AUC. However, to minimize bias, this approach can select noisy features that have low predictivity, leading to low overall AUC. Another approach is to select features that most improve the overall AUC, hoping that this increases the AUC for all groups. However, when features are more predictive for one group compared to the other, then this approach can result in classifiers with high bias. The question is, which features should you as a data manager select in order to ensure that the output classifiers have both a high AUC and a low bias? Our approach is to select features iteratively. At each iteration, we first identify the group with the minimum AUC and then select the feature which most increases the AUC for this group. We call this procedure FairAUC. FairAUC seeks to increase the AUC of the group with the minimum AUC at the current iteration. We prove that this ensures that FairAUC strictly increases the AUC of the lowest AUC group by at least a lower bound determined by the first and second moments of the features. And moreover, it does not decrease the AUC of any other group in any iteration. Further, if at any iteration the lowest AUC group changes, then in subsequent iterations, FairAUC will select features that maximize the AUC for the new lowest AUC group. In terms of applicability, FairAUC can also be used as a heuristic with classifiers beyond generalized linear models. In this case, FairAUC does not need access to the internal details of the algorithms, but only requires access to the input features and the output confidence scores of these classifiers. I encourage you to look at the longer talk for a discussion of how FairAUC may be used in practice. Empirically, we evaluate FairAUC on both synthetic datasets and the compass data. The synthetic dataset we use is generated according to a binormal framework. It has 50 features where half of the features are informative and the rest of the features are informative noise. On the compass data, we consider two protected attributes: individuals whose age is at most 25 years and individuals whose age is at least 25 years. On both data sets, we find that FairAUC decreases bias and improves the overall AUC. In comparison, max AUC has a higher bias and a similar AUC as FairAUC, and other baselines have a much lower overall AUC, and a similar bias as FairAUC. I encourage you to check out the paper and the longer talk for much more detail. And to conclude, I'll note that it's important to consider FairAUC as part of a broader system of mitigating bias that in particular combines it with pre-processing, in-processing, post-processing algorithmic approaches.